Recently, I had asked for an MCQ on my social media platforms, a problem-based MCQ. Data is given and you are expected to solve by applying some equation, some formula. And every week we are going to see such MCQs, discuss these MCQs, because the Indian medical education system is gradually moving towards these kinds of exams where more of clinical MCQs or problem-based MCQs are likely to be asked. This was a simple one. It required simple problem-solving ability. But before we start, let me tell you, very often the students of medicine, they come and say this to me, that sir, maths requires problem solving ability. We wanted to avoid maths and therefore we opted for bio and thereby the medicine, biology and physiology, medicine. So again we are required to solve the problems and all. Yes, it is like that. For instance, in the case of diagnosis, you have taken up medicine, you need to make the diagnosis, and for diagnosis you will need this kind of a approach, problem solving type of approach, and therefore let's develop that. Okay, this was the MCQ. Analyze the following data: tidal volume 400 ml, respiratory rate 20 breaths per minute, ventilation perfusion ratio 1.0, and cardiac output 5 liters per minute. How much will be the dead space volume in this patient? That's the question. Okay, and I had given a hint also. Your starting point for the MCQ should be ventilation perfusion ratio 1.0. If those who could take up that hint could answer the question. Okay, many students have answered this question. So let's understand how to solve such MCQs. What should be the approach? Remember, whenever you see such MCQs, always look for such hints first. Look for something as a starting point. From where will you start? Okay, and then take the things from there onward. Let's start. Before I come to the MCQ and how to solve it, I'll just take a theoretical background to it. Here is the alveolus. Here is the pulmonary blood, the blood vessel. We inspire tidal volume, the amount of air that we breathe in or breathe out with each quiet breath. That's tidal volume, and it is roughly about 500 ml. I'm not talking about MCQ right now. I'm just giving you a background of all this discussion. So let's say this is 500 ml. Out of this 500 ml, roughly 150 stays in the dead space. Okay, let's take, for the sake of simplicity of calculation, let's say 100 ml stayed in the dead space, and which means 400 ml reaches the alveoli and ventilates the alveoli. So here in this case, we inspired 500 ml. Out of that, 100 ml was wasted in the dead space, and 400 ml actually reached the alveoli to take part in the gas exchange. Right? So this will be alveolar ventilation in one breath. How much? Let's say 400 ml in this case. Okay. So if you know this and you know this, then you can calculate the dead space volume. Simple. This is what is required in this particular MCQ. If you want to just calculate it further, look, respiratory rate is the number of breaths per minute. Let's say 10 breaths per minute is the respiratory rate. That means in each breath you inspired 500 ml. Then in 1 minute, how much will you inspire? 5 liters. That will be respiratory minute volume, or its minute ventilation. Then alveolar ventilation, in one breath 400 ml is reaching the alveoli. then in 1 minute how much ventilation will occur in the alveoli? If the respiratory rate is 10 breaths per minute, okay, in each breath 400 ml reaching the alveoli and 10 such breaths per minute, that means 4 liters per minute will be the alveolar ventilation. So now it's clear, if 5 liters per minute is the respiratory minute volume and out of that 4 liters per minute is reaching the alveoli, then the remaining 1 liter will be the dead space ventilation. It will be lost in the dead space, and per minute therefore 1 liter in this case will be the dead space ventilation. It never reaches the alveoli, right? So this is what is required to be known. Now coming to the ventilation perfusion ratio as the starting point. Let's see what was the data given. Tidal volume was given as 400 ml. So in each breath we inspire 400 ml. Respiratory rate given was 20 breaths per minute. V to Q ratio is 1.0 and cardiac output 5 liters per minute. Now look, focus on this ventilation perfusion ratio. What is this ventilation perfusion ratio? It is the amount of air that ventilates the alveoli every minute upon blood perfusion to those alveoli every minute. This ratio. You can see in the diagram again that this much air reaches the alveoli per minute to take part in the gas exchange, and this much is the blood flow to those alveoli per minute, so that the gas exchange can occur between alveolus and the pulmonary blood. Okay. How much is the blood perfusion? It will be the same as cardiac output. Blood perfusion to the alveoli, that is Q in this equation. This will be same as the cardiac output, because right ventricle will pump 5 liters of blood every minute, which is the cardiac output, and it will be same as left ventricle. Left ventricle will also eject out 5 liters of blood every minute. 5 liters is the cardiac output, means each ventricle is pumping out 5 liters of blood. So right ventricle ejects 5 liters per minute, and that much is the blood perfusion in the lungs. That blood ejected by the right ventricle will circulate through the lungs and come to the left side of the heart. That is every minute. So therefore cardiac output given in this data 5 liters per minute, it will be the blood perfusion in the lungs. Okay, 5 liters per minute. That's one. And they said ventilation perfusion ratio is 1, exactly 1, which means how much will be the numerator? Come on, say it now. If this ratio is given as 1 and this denominator value is known to us, how much will be the numerator? 5 liters per minute. That means from the given data we have derived one thing, and that is alveolar ventilation per minute is 5 liters. All right. Where is the data? Yes. Alveolar ventilation will be 5 liters per minute. All right. Okay. So we are aware that alveolar ventilation per minute is 5 liters. This much air is reaching the alveoli every minute. Okay. 500, I beg your pardon, 5000 ml is the air reaching the alveoli every minute. How much is the respiratory rate given in the data? 20 breaths per minute. So if we divide 5000 by 20 breaths per minute, then we will know how much air is reaching the alveoli in each breath. Okay, 20 breaths are happening in 1 minute, and in those 20 breaths 5000 ml, that is 5 liters air is reaching the alveoli in that 1 minute. So in each breath, how much will it be? Let's divide it. Okay, answer is 250 ml. So you can see here, answer is 250 ml. That means 250 ml in the given data, 250 ml air is reaching the alveoli. That is clear now from the calculation. And they had given tidal volume as 400 ml. It means in each breath we inspire 400 ml, out of which 250 ml is reaching the alveoli in each breath. Yes, we calculated that. So how much must have been wasted in the dead space? Come on now. Answer is 150 ml. 150 ml is the air that is wasted in the dead space, and 250 is reaching the alveoli. Okay. That means the dead space volume is 150 ml. And remember, there is something called as dead space ventilation also. So if you multiply 150 into respiratory rate per minute, then whatever it is will be the dead space ventilation per minute. However, that was not asked. What was asked in the MCQ was what is the dead space volume, and this should have been your approach to solve this MCQ.